Okay, so welcome to week 4 of Astronomy 101. Thank you all for joining. I know it's been kind of a rough week for a lot of people, but you all are doing great and you're doing the best you can, and I'm proud of you, and thank you for coming to spend some time with me studying astronomy. Thing I'm going to do, if you have been watching these on YouTube or if you're watching it now on YouTube, I am starting to cut it off after the lecture. So we're shooting for like a half-hour class and then a half-hour kind of more open Q&A. I'm going to stop the recording after the class and post that to YouTube. So if you are watching this after the fact, it will end after the full material, and then we'll get into random questions that I've got from people throughout the week. But if you do have questions, feel free to leave a comment, and I do check those. I do respond to those. And then you can always message me, and I will respond to them here. So, thank you all for being here. What we are going to talk about today is ancient astronomy. So we are going to be discussing, we're going to kind of take a mind break from doing all of that local sky stuff. There is going to be one thing that's a little bit mind-bendy that takes some wrapping our head around. But then we're going to get into more ancient astronomy cultures and the evolution of thought about why our universe is shaped the way it is, particularly with our solar system, and how those thoughts evolved and changed over time, as a little bit of a down week. And then next week, we're going to be getting into some more of the sciencey stuff. This is where there will at least be diagrams. But I promise we'll go through it slowly. But today it isn't too bad. First off, I do want to mention, in terms of what's in the night sky this week, it is a full moon tonight. This is Friday on June 5th. It is also, the moon is also experiencing what is called a penumbral lunar eclipse. So if you remember from our, there we go, last week, we talked about seasons, we talked about lunar motion and phases, and we talked about eclipses and solar and lunar eclipses and umbral versus penumbral. So if you are paying attention to things that say like this, what's in the night sky this week, hopefully it should make more sense when you see that there is a penumbral lunar eclipse happening. If you recall, umbral is that sort of main dark shadow, and penumbral is sort of the side shadow that's made. So when it's just one portion of either the planet or the moon that's the shadow is carrying on, the umbral is when they're combining and it's like extra shadowy. And a lunar eclipse, this is where the Earth is blocking the sun and the moon. So the moon is in a full moon phase, so the sun is directly hitting it, and it's passing through the Earth's penumbral shadow, which remember is this outer portion of the shadow. That's the word I was trying to think of. It's the outer portion of the shadow. It's not available in North America. You won't be able to see it. It'll already have it either has passed through or will already pass through or is passing through. Time of night stuff. But it's mostly visible sort of throughout kind of Russia down Australia-ish Africa region at night. Again, it's not a particularly spectacular one. It'll just be a little bit slightly darker than it is. Maybe a little bit red, just if there's some of the shadow that's passing through. But not, like I said, not a full lunar eclipse and not available in North America. Titan, the Saturn's moon Titan, is going to be due south of Saturn on Saturday. And so if you have a telescope, it'll be kind of easy to see then. Monday is the 395th birthday of the astronomer Cassini, after which the ring patterns on Saturn, as well as the Cassini imager traveler. It's been a week. Was named. So pretty pictures from Saturn were taken by Cassini. And we are also A probe. There we go. Yeah, it eventually landed in Saturn, went through Saturn's atmosphere. On Thursday, about a half hour after sunset, you are going to be able to see Mercury in the sky about 10 degrees above the north-northwest horizon. Mercury is hard to see. That's what we're going to talk about today. But on Thursday, half hour after sunset, it'll be about 10 degrees. So if you're remembering all of this stuff, you should be able to see it. If you stick your fist up like that, north-northwest, about a half hour after sunset, you can see Mercury there. So, and that being said, let's dig into what we're talking about this week. So, we talked about seasons last week. Remember, seasons are caused by the tilt of the Earth. The Earth is tilted on its axis about 23.5 degrees. And when the bottom part is tilted towards the sun, that's summer in the southern hemisphere, winter in the northern hemisphere. And then when it's facing the other way, such that the sun is over here, more of the sun is facing the northern hemisphere like it is right now, and less on the southern hemisphere, so they're experiencing winter. As it's on the other side, that's sort of spring and fall, when it's about equally spread out across the planet. We talked about lunar motion and phases. So the moon goes around the Earth about once every 29.5 days. And based on where it is relative to where the sun is, we get these phases. Because you think of the moon as basically a giant mirror. And based on the position of where the sun is to how much it's hitting the moon, and then that is reflecting back to us. That's how the moon goes through its phases. And then, like I said, we talked about solar versus lunar eclipse. Solar eclipse is when the moon passes between the Earth and the sun, blocks out part of the sun. A lunar eclipse is when the Earth passes between the moon and the sun and casts a shadow onto the moon. That because the moon is a mirror, we're able to sort of see that effectively. And then umbral versus penumbral is what we talked about with that sort of full shadow versus partial shadow, makes different types of eclipses. So going on from that, we're going to talk about planetary motion today. And this is sort of leading into this ancient astronomy topic that we're going to talk about. So these are the planets that you're able to see with the naked eye. You could see Mercury. So this is all, without a telescope. You can see Mercury in the night sky. It's pretty rare. It's hard to see it just because it is so close to the sun. And like I said, this week on Thursday, you should be able to see it about a half hour after sunset, but it's going to be setting. It's going, we're rotating away from it, so it's going to drop pretty fast as well. But you can see Mercury. You can see Venus. Venus is probably the most well-known one. It's very bright in the early evening or before dawn. It's that sort of morning or evening star. It's really, really bright. And even with the naked eye, you can kind of convince yourself, although sometimes I wonder if I'm actually seeing it or if I'm just convincing myself I'm seeing it. Hey, Andrew. You can actually see Venus having phases in the same way that the moon reflects light. You can see, depending on the alignment of where the sun is to Venus, the sun hitting it and then coming back to us. So sometimes you can see like a half or a crescent Venus, and it's pretty cool. Hard to see, but like I said, even with the naked eye, you can kind of convince yourself that's what you're seeing. You can see Jupiter. When it is visible at night, it is the brightest object after the moon and Venus. So it's pretty bright because Jupiter's pretty big. Mars, you can see, even though Mars is closer than Jupiter, Jupiter is a lot more reflective because of its atmosphere, and then it's also much bigger. But Mars, you also can see, it is visibly red. You can tell that, if you can tell it's a planet, you can tell that it's Mars because it is red. But red stars also look very similar to that. So if you are looking up randomly in the night skies, I hope some of you are starting to try to do. If you look up and you see a red object, that can fall into the possibly Mars category, but definitely get like an app on your phone or a star chart. I think we mentioned I use Skyview as a free one, and just point it up there and see if it is actually Mars, because it could be a red star. And then Saturn kind of is about the right brightness as a lot of the basic stars that we see. And again, even without a chart, the first thing you can do for all of these, but particularly I think I use this fact the most with Saturn, is, because it seems to be like a lot of the stars, is that planets don't twinkle. And this is kind of a weird thing to think about, but the way it works is because the stars are so far away, they effectively are single points in our eye. Think about it like they're a single pixel. And the planets are a little closer, so they're like 2 or 3 pixels. And it doesn't matter that much to us, to our eye. It's hard to distinguish that a little bit. It's mostly the brightness that we go off of. But because planets are like 2 or 3 pixels wide versus a single pixel, when the atmosphere is between, the atmosphere is always between us and the stars or the planets, due to the atmosphere, that single pixel, that star, is going to appear to jump around a little bit. That single pixel is going to jump around, whereas the multiple pixels, I'm just using pixels as a reference, but the multiple pixels that the planets take up don't appear to jump around because the atmosphere isn't wiggling their light waves enough. I hope that makes sense. But that's always a good sort of sanity check as well. And definitely something I always do when I'm trying to find Saturn is if I think I found it, if I think it's in the right position, I know kind of where it's supposed to be, it's in around the zodiac, so that pattern of, you know, where our solar system lies, then I check to see if it's twinkling or not. And if it's not appearing to move around a little bit, twinkling just being like jiggling, then I'm like, oh, that might be a planet. So you can do that for all of these, including Mars as well. You can do that with Mars too. So now we're going to transition with that fact, thinking about kind of our understanding of the night sky. So bridging that observation of our local sky into how people used to observe it and the things that they learned about it and where that knowledge came from and went. The term planet, these objects, these, 5 planets that we can see with the naked eye, ancient cultures were able to see this too. And particularly the Greeks, at least in sort of Western centralized cultures, we kind of look to the Greeks as a lot of the main sort of culture and era that established a lot of astronomy that we understand. We are getting to that. Thank you. No worries, Andrew. I appreciate that. That's the next one. So when we're talking about the Greeks, planet, the term planet actually comes from the ancient Greek word for wanderer, because they wandered in the night sky. Now, the reason I didn't mention that up front when we're talking about how to find them is because they vary night to night to night. So it's not going to help you much if you're just like looking up at the night sky. You're not going to see it visibly moving against the background. It's just going to be in a slightly different position the next night and a slightly different position the night after that compared to the background of the stars. So this, and so that's where that wanderer came from. They had the background of all of these stars, that celestial sphere, but then there were these 5 objects that they could see that looked like stars, but every night appeared to be in a slightly different position as they went through. So you may have heard, especially, this sort of like phenomenon goes in waves, and I mean, I have friends that swear by this, and they are great friends, and I love them, but they swear by this, that the apparent retrograde motion, Mercury's in retrograde, or Mars is in retrograde, explains a lot of stuff. Okay, let's talk about what retrograde actually means. I'm not going to disparage any of that stuff because this is very different than the astronomy aspect of retrograde motion. So if you believe that planets being in retrograde orbit affects your life and all that, just you do you. But we're going to talk about where that comes from. And this is the part that's a little bit hard to wrap your head around. So stick with me. And for me, even, it always takes one of those. Okay, what's actually happening again? So this is, as we talk about the planets progressing through the night sky from night to night, they usually move in an eastward direction through the zodiac. So if you're thinking about the sun setting, right, it sets in the west, a planet will be here. The next night it'll be slightly further east. The next night it'll be slightly further east. just with respect to the background stars. And I say specifically zodiac because remember, those are the constellations that lie within our plane of our solar system. So if you have our solar system, you project it out against the sky, you're going to get the zodiac constellations. So they're going to move slightly eastward through the zodiac, but occasionally they go in the opposite direction. That night to night, they'll slightly start moving westward each night, and then they go back eastward. And it's weird, but this is where it comes from. It's actually fairly straightforward. I'm going to leave this up for a while so you can try to wrap your head around it. This is Earth to Mars. And if you just think about it, it's basically that Earth is closer to the sun. Mars is further out. That means that Mars is orbiting slower. And we'll go into why next week to do with planetary orbits and everything. But Mars is further out, so it orbits slower. As Earth passes by Mars in its closest point of passing, you can see on this background part here, it appears to go slightly backwards. And then it continues on. And this right here is the part that's the hardest to wrap your brain around. So look up as many images, as many videos as you can, as you want. I get it. It's hard to sort of understand. Typically, when I teach astronomy, what we would do is clear out the entire classroom, and we would literally just have people like walk around in circles and walk around in circles outside of that and map when people appear to be moving backwards relative to where they are. But I feel like this image kind of captures it pretty well. And because we have these circular orbits that are happening both inside and outside, the planets are passing each other as they're going by. So sometimes you have it where the planet is passing on the other side of the sun. And so while you might not be able to see most of it, there will be points where it appears to be going in the opposite direction. But it just has to do with these circular orbits. And this retrograde motion is what effed everything up when trying to figure out and model the night sky for ancient astronomers. This apparent retrograde motion broke everything from the ancient Greeks all the way up to Copernicus and beyond, because it didn't make sense. It just didn't. They had all these great models for, this celestial sphere, the motion in the night sky. There are these planets that seem to move in certain directions, but then they go backwards and then they go forwards again. What is happening? So going from this is where that sort of, trying to figure out where we are, what our solar system looks like, this is where that comes from. So the question is, if you can fairly easily model this with just basic geometries, just thought experiments of walking around in a circle and seeing apparent backwards motion, the Greeks were on their game when it came to science. And why didn't they accept a sun-centric model? This idea that Earth is going around the sun and that these other planets, these 5 objects that were wandering in the sky, weren't also orbiting the sun. Because as soon as you do that, you can very easily replicate this retrograde motion. So why didn't they do that? They had kind of 2 explanations for this behavior, and why they wouldn't necessarily accept this model. So the first one has to do with parallax that I'm about to talk about. And it's idea that the stars, the background stars, are so far away that they wouldn't be able to accept the parallax, that they wouldn't be able to actually see with the naked eye the parallax. And then the other option was like, okay, well, then things are just moving weirder than we think that they are, that it's not a sun-centric model. This idea of parallax in the celestial sphere, for the Greeks, and the way they saw the night sky with this local sky, because as I'm introducing all of this to you, we started thinking about the local sky in the same way that the Greeks had seen that. They had, come up with names for it. They'd observed the behavior, and then this retrograde motion and these planets were being observed, and trying to model that and figure out, unpack our local sky and figure out the world in which it lives. Parallax is the apparent change in position as the Earth, for example, is going around the sun. So at one point in the year, you can look at a star and you'll see it in this position if it's closer to you compared to all of these background stars. So this star is really close to you. The yellow star is close. And in January, it'll look like it's here compared to all these stars. In July, then that close star is near you, and it's going to appear on the other side. So as the Greeks were thinking about this retrograde motion, and actually, legitimately, there were astronomers, one of whom I have a name written down later that I don't have at hand right now because I never remember it, did actually propose at like 500 BC that there was a sun-centric model. But then this idea of parallax came up. And it really had to do with the fact, so it was like either the stars are too far away and we can't observe it, which is true. Space is big. It's hard to wrap our brain around how big space is. But particularly this fell apart for them because of the celestial sphere. Remember, they thought that it wasn't that these stars are all distributed throughout our galaxy and our universe, but that they all lie on a dome. And that meant that when Earth was on one side of the dome, you should be able to see an angular separation much different than if you're on the other side. So if you're on one side of the dome, these stars closest to you are going to appear further apart than they do way on the other side. They're going to appear closer together. And we had talked about those angular distances. If there was a celestial sphere that wasn't massive, then you should be able to see these angular distances change as the Earth goes around the sun. Because they didn't see that, and they dismissed out of hand the idea that it could possibly be that big, which is what is true, they said that, okay, there's no way that Earth is going around the sun. Because if it was, we would see the patterns change on the celestial sphere. We would just be close to versus far away. It would look further apart, and it would look closer together as we went around. So they dismissed it. And they just said, no, okay, that there's no way that Earth is going around the sun. So good thought, good try, people. Let's carry on with trying to figure out the night sky. So we talk about scientific thinking in these ancient cultures. I think a lot of, especially people who have kids or have been around kids, you do understand that scientific thinking comes naturally. It's just, you do something happens, and you try to figure out cause and effect. That's scientific thinking. You start learning that if you tip something off of a table, it's going to fall. Why is it falling? Trying to unpack all of that is very natural scientific thinking. And because of this, astronomy stretches deep into antiquity, beyond the Greeks. It goes way before that. The Greeks were just kind of the first to try to figure out, at least in a Western culture, try to actually model what was going on. But the sort of discovery of patterns and all of this behavior has gone way, way back, as long as, humanity in some form has been around, because scientific thinking comes naturally and there's survival to it. And there's also not a lot to do in the evening when you don't have electricity. So you learn the sky. And the practical benefits to astronomy, Hypatia. Ooh, look up Hypatia. I mean, I wish I took an entire semester in ancient astronomy. Like, there's so much cool ancient astronomy stuff out there. There's great books. There's great, definitely. Just search ancient astronomy and your glass will be full of awesome people and facts and stories. But the practical benefits of studying the night sky and learning about it, even in ancient times, one of the first things that people were able to do is predict rainy seasons. And this is awesome. This is hard to kind of wrap your brain around, but this is from ancient African cultures. They were able to study what they called the horns, what's been translated to be called the horns, of a waxing crescent moon. So remember, waxing means it's getting bigger, but that's at a very specific phase throughout the month. That means it's on its first, going from new moon to a first quarter moon, waxing crescent moon, and what direction the horns of the crescent are facing. And they realized that there's a pattern to this. Andrew, you're on top of this, man. That's the next slide. But they realized that there's a pattern to these, to the crescent moon. And through that, you'd be able to predict when the rainy season would be month to month. You'd say, okay, because it's at 25 degrees now, next month there's going to be more rain. And so we're able to do that. You can measure time. We talked about months and seasons. It's a cyclical nature. So even if you don't understand why the seasons or the months are happening the way that they are, you can still use the night sky in order to measure them. We even have, our 7 days of the week are named after astronomical objects. You have the 5 planets that you can see with the naked eye, and then the sun and the moon. So, no worries, Andrew. That's what we're here for. I love it. All the backgrounds are welcome. So the sun and the moon are sort of our default objects, and then those 5 planets that we can see with the naked eye are what make up our days of the week. And then you have 4 weeks for a month, and that's 1 lunar cycle. And then, you have years that you base on your cycle of the seasons and the motion of the sun in the sky. So I love that. I love it. That's one of my favorite charts. And then time of day, even just day to day, you can see the sun move throughout the night sky or through the sky, and you're able to figure out what time it is, and then how high it's getting can tell you about, where it is at noon can tell you kind of where in the year you are and where you are on Earth. So pretty cool. I got that from Assassin's Creed. Yeah, it's a month. It's a month. And no worries, Andy. This will be recorded, as you know. All right, so as Andrew mentioned, Stonehenge is a way that they use to mark these seasons, because you can the lunar cycle's fairly easy to just see. And if you match it for maybe a couple months, you're going to look at it and you're going to go, oh, all right, I know what's happening next. The seasons are on a much bigger scale, so it's still hard. It's much harder for us to be like, okay, so when is it going to switch and start going back? And that's why these ancient structures were built, because they could tell that at one point it stopped, right? It rose, the sun rose every morning further and further north, and then it stopped, and then it started moving back. That's the solstice that we talked about last week. They built structures to mark where that stopped, to say, okay, after it rises here, every subsequent night or day, it's going to get shorter and shorter and shorter, and we're going to be going through summer into the winter. So Stonehenge has that clearly marked, where it rises right in line with the heel stones. And then this is the sun dagger. This is kind of sad. So it's pretty cool. It actually measures multiple points. It's built to measure multiple points throughout the year, such that the summer solstice, it's straight through the middle of it. You have points where the spring and the fall equinox will sit on it nicely. And then the winter solstice, you actually get 2 beams of light that cover both sides. It was discovered in 1977. And 12 years later, there had been so many visitors there that they had disrupted the ground so much that the rocks actually fell out of alignment. So you can't go see it do that anymore, unfortunately. It only took 12 years of us to do that. That's a good question. I should have had that fact ready. I always just know it as the sun dagger. Sun dagger is in Chaco Canyon, New Mexico. It's a Pueblo, the Pueblo people. Actually, Pueblo culture has a lot of ancient astronomy. They have the whole culture was just all of their petroglyphs. There's a lot of keys to astronomy there. That culture was really, really good at marking things like this. So, agreed, Andrew. Sad face. Sad robot face. Okay, so this Greek geocentric model, they were thinking about this. And Anaximander, I think, was the guy who first thought maybe that the Earth was going around the sun. But anyway, they had this celestial sphere. As the Greeks were continuing to think about this through like 600 through about 400, BCE. They thought that like maybe it was just rings. They did actually propose, Thales and Anaximander thought that maybe the Earth was actually a cylinder, because they did recognize that as you moved up in latitude, the night sky changed, but it didn't change as you moved in longitude. So they thought that Earth was a cylinder, which is kind of cool. And then we got Ptolemy. Ptolemy was the first one to try to actually model the retrograde motion. So what he thought is that Earth is at the center. Again, remember, the Greeks dismissed this idea that Earth went around the sun because the stars didn't change position throughout the year. And they thought that the celestial sphere, as you're close to or far away the edge of it, the stars would change. So they dismissed that. Earth is at the center for them. And then Ptolemy came up with this model where you get this these orbits as they go around. And this would explain that retrograde motion. It's a rough model. It's a rough model. The other thing to note here, too, is that a lot of what drove the difficulties, particularly as we get sort of a few more, like 1,500 years later, is this idea that perfect circles exist. The ancient Greeks, even they had that cylinder thing, but a lot of the ancient Greeks as well did believe that Earth was a sphere, simply because that was like the beauty of mathematics and what they were studying. So they believed that like these orbits were all circular, that Earth was a sphere. And then this was Ptolemy's model to be able to explain retrograde motion. Again, put Earth at the center. You have to have weird orbits to explain how the planets change direction every night in the night sky. Fun side note, Aristophanes estimated the size of the Earth down to like, I think he got an answer of like 40,000 kilometers circumference, and it's 42,000. Simply by going north and south and recognizing that on the summer solstice, the sun is in a slightly different position, measured those angles, and then was able to be like, okay, if there was a 7-degree difference between here and here, then that's 1/7 of like 7 out of 360 degrees. Measured the distance between those 2 points that he had traveled to, said, okay, that's 7 out of 360. Multiply that into a full circle, and he was only 2,000 kilometers off, which is pretty awesome in 240 BCE. Awesome fact. All right. Copernican revolution. We're now at the end. So the Ptolemaic model of the solar system, this idea that Earth was at the center, planets went around that. And if you notice, actually, the sun, so you had Earth, then the moon, then Mercury, then Venus, then the sun, then Mars, then Jupiter, then Saturn. And they all made circles, and Earth is right at the center of it. This lasted for 1,000 years, easily 1,500 or 2,000 years almost. They were quite happy with that, ish. Copernicus came along, Polish astronomer. If you go to Krakow or other, I think Krakow was where I saw a lot of stuff. Tons of statues of Copernicus. Very popular dude. They had this Ptolemaic model, right? This idea, that solar system that Ptolemy had developed to put the Earth at the center and explain retrograde motion. From that, they had built out these tables of planetary motion that said, okay, if, here's what's going to be this day, here's what's going to be this day, and you just chunk through. And they were getting pretty inaccurate. Things were breaking. Things were not good. But literally, like, this is how it was. By the time Copernicus showed up, astronomers were like, yeah, those tables are wrong, but I don't want to do it. Was actually the culture of just like, it's not working, but it's going to take way too much work to actually try to figure that out. So Aristarchus, that's the guy who thought that the sun was at the center. And Copernicus dug it out. He was like, all right, F that. Like, I don't want to try to figure out Ptolemy's tables anymore, because this is a hot mess. This is a hot mess. This is nonsense. That one guy thought that the sun was at the center. So let's dig that out. Let me try looking at this. He did discover really solid geometric relationships that was able to calculate the period as we were going around the sun and then the distances. The issue is that he made all these observations, put the sun at the center, and it didn't work on from day to day because he had assumed perfect circles as well. Everyone just thought the universe is so beautiful, it must all just be perfect circles. And so his tables, while the geometry worked and he was able to make these predictions and he built out these tables as if it was a sun-centered model that worked-ish, but then they were off because he had assumed perfect circles. We're just going to do these bios of these main people during this era, and then next week we're going to get into the actual kind of science that they developed. It's going to bring back a lot of memories for you if you've taken Astronomy 101. But Tycho Brahe. Tycho Brahe. I got to admit, I kind of have a crush on this dude because he's such a hot mess of a human being. Just read about him. We have dug up his body twice to figure out what was up with this dude. So he was dug up in, I think, 1901, or I should say his body was exhumed in 1901, I think, and then also in 2010 to try to figure out, first, what his nose was made out of, if he had died of poisoning. It's just, this guy was a beautiful, crazy, hot mess. Some of my favorite... So I'm just going to share my Brahe facts before I actually get into his contribution to astronomy, because that's really the most important thing, but the amusement can't be forgotten. Awesome, Valencia. Please share with people if you get it, because that would be awesome. So indeed, Tycho Brahe loved astronomy, came from a fairly wealthy family, so he had access to education, wasn't necessarily supposed to go into astronomy. So legend is that he got a celestial sphere that he studied, kept it secret for ages. He got into a duel with his third cousin twice when he was 20 because he thought he was a better mathematician than his third cousin. In their second duel, they decided to do that in the dark, and a sword cut his nose off. So he made a replica nose out of, the legend was gold and silver. When they exhumed his body in 2010, it is measured to be brass, and just stuck it on with plaster. So he had a brass nose, which is just awesome. He kept an elk for a pet. He would take this elk, fully grown elk, to parties and get it drunk as well as he did. Sadly, I mean, this is content warning, animal cruelty. The elk died when it fell down the stairs because it was drunk. His best friend was named Jeppe, who was a little person that Tycho Brahe believed to be psychic. And he would have him sit on the floor next to him during meals and then feed him scraps of food as Jeppe fed him stories and ideas about people. He also, transitioning to Tycho Brahe as a astronomer, he hoarded his data. He kept it all close. He was pretty paranoid about this and wanted all of the credit. And right, fair play, Brad. And his annual income was 1% of all of the money in Denmark every year. And it is rumored that, this is a hard rumor, but like I said, hot mess of a human, hold those rumors close just from the hilarity, that Hamlet is partially based on Tycho Brahe. That there's a lot of allusions to Tycho Brahe in Shakespeare's scripts, and there's a Rosencrantz and Guildenstern tie as well. And it's just a crazy man. So his story when it came to astronomy is that he believed that these tables, all of this stuff that was going on, he's like, we just need better measurements. We just need better data. He did love astronomy. He had gone off of Copernicus. So Copernicus had started to update these tables from Ptolemy, but again, putting the sun at the center. Even when he did that, there was supposed to be, so you can see, I don't know if you were paying attention before, but there's about almost 100 years, no, about 50 years-ish later between them, 50 to 70 years between them. He had predicted a pretty good alignment of Jupiter and Saturn, and it came 2 days after Copernicus had predicted that it would. So he was like, we just need better data. We need to measure stuff better. They don't have telescopes at this time. In 1572, he did observe a new star in the sky, which they called a nova, which we now know was a supernova, which we will learn about later. And then he got money and support to build a naked eye observatory that was so good, you can see sort of a mock-up of it here on the side, that it was actually able to make measurements in the night sky with the naked eye accurate to less than 1 arc minute. So remember, you take a degree, a single degree, divide that into 60. They were able to measure 1/60th of 1 degree with the naked eye difference and took copious notes. Again, he was a data dude. Like, he loved his data. I get it, man. I get it. And he basically believed, with all of this data that he took, he was like, okay, the best I can come up with, because there is no parallax, there's no change in the celestial sphere, the position of the stars, that the sun must orbit the Earth, and then the rest orbit the sun. So the sun goes around the Earth, and then all the other planets orbit it. It's a bit of a wacky theory, but that's how he explained all of the data that he got. His biggest contribution was just the amount of precise data that he took without a telescope. Then came Johannes Kepler. So the story between Tycho and Johannes Kepler is that it was not good. Johannes Kepler was Tycho Brahe's student, and he was so frustrated with Tycho Brahe's data hoarding that rumor was that he poisoned him. Then there was another rumor that Tycho Brahe died of poisoning because he slept with the Queen of Denmark. All of those were disproven, mostly in 2010 when they exhumed his body and discovered that he probably died from an exploded bladder, which doesn't sound much better. But they did not have a healthy working relationship, I suppose. We can just put it this way. Hot mess is a good way of putting it. Johannes Kepler was so invested in figuring this stuff out, and they just couldn't get... I agree, Adam. I agree. Tycho Brahe, especially in the data world, needs a little bit more respect because we just love him. He was holding on to these perfect circles, and he had all of Tycho Brahe's data once he died, which is a whole thing. And he was getting these discrepancies between what was predicted, what they were seeing, and by what I mean by what they were seeing, I mean going through all of Tycho's detailed data measurements. And he's, yeah, Benny, exactly. He found an 8 arc minute discrepancy in sort of predictions to data. Now remember, 8 arc minutes, take your degree, divide it into 60, 8 arc minute discrepancy. He was holding so close onto these perfect circles, and he's quoted as saying, if I'd believed that we could ignore those 8 arc minutes, I would have patched up my hypotheses correctly, or accordingly. But since it was not permissible to ignore, because the observatory and the data was so good, those 8 minutes pointed the road to a reformation in astronomy, which is 100% true. The fact that he did not dismiss Tycho Brahe's meticulous data taking and took those into account and instead gave up that perfect circle idea, that changed all of astronomy. So really, when we talk about the resistance to the sun-centric versus earth-centric models, or geocentric models, from an astronomical standpoint, it wasn't so much this fear of the religion, although Galileo certainly had to deal with a lot of that, but within the astronomy community themselves, it was their resistance to the idea that everything wasn't in a perfect circle, that they had such a hard time accepting that the universe wasn't just perfect, that slowed down a lot of that progress. And it wasn't until Johannes Kepler let that go that they were able to change all of astronomy, which is what we're going to talk about next week. So with that, if you do have any questions on stuff I talked about, feel free to drop them in the chat. I am going to stop the recording now. I'm going to hang on the live stream. If you are watching this as a recording after the fact, please leave a comment in the questions down below. I will respond there, and I will also bring them up here next time. And you can find links down below so you can join us Fridays at 1 p.m. Pacific time.